Okay, let me start now this lecture of today. Considering a topic which belongs also to another course, dynamical systems. And in any case, it's important to repeat because we will see that to design controller, in particular PID, lit lig. We will see what I intend with this. PID is known a little bit from different courses, or in general, you heard about PID controllers, about the rest, about different controller. We will see here together. But in particular, we will see that PID controllers can be seen as particular form of different, more general controllers, which are used in automation. We are here to consider some control structures which are used in automation. Nevertheless, let me start with this presentation. I don't know if I will use the presentation until the end, because here, as I told you, is in a lecture which belongs to different courses. We don't need probably everything, but it in my opinion makes sense to flesh out or to tell you a little bit about the Laplace transform and how I can use it. Laplace is known from math a little bit, but you probably, I suppose that you didn't apply in modeling. Okay, this makes sense because last semester, I remember well, I didn't consider the Laplace probably at all, because I invested more time in sliding mode control, I think. Okay, Laplace transform. Here's a little bit what I would like to tell you, even though quickly. It could be that this last 2 points, I will just point 6 and point 7, I will just flesh out, because in any case, this semester I have more time to lecture more, because typically I start in January. We can see also from here in automation, of course. But in any case, I think these 2 points can be seen using some exercises. This means this presentation probably I will tell you in detail. I don't know how much in detail until point number 5. The material which I will use for the course is here. I will upload in my study. We have exercise, which we have many aspects which I will consider more in depth, exactly as I told you now, using exercises. Let me start with the definition of Laplace transform, and then we will see properties, but very quickly. Extremely important, the point 3, concept of transfer function. Probably you heard about the transfer function a little bit in math, but you didn't apply in, let me say, in practical applications. Transfer function is connected with the modeling, as I told you now, modeling through the transfer function. And then we will see a little bit this calculation response of a system using the transfer function, because the central point of this session, of this lecture, let me say. Okay, look at this. Probably about the definition you heard in math. I don't spend energy. I don't want to spend energy to repeat it, but it's basically a parametric integral. Please pay attention. Parametric integral. This means it's an integral in which we have a parameter is an integral over time. The domain of the integration is time. We see dt. Again, the integral between 0 and infinite plus infinite in accordance with the definition of a function. This is the Laplace transform of a function. Laplace transform of a function f. Could be sine, could be cosine, could be sine of t, of course, omega t. We say cosine of omega t. Could be any kind of function which we learn in math. Multiply, e is an exponential function. In some books you can find ex p, exponential, but e is the exponential function. Up to minus st. This means the parameter is s. If you remember what I told you exactly now, it's the parametric integral. This means at the end we can see from this definition or from this equation that we will obtain, starting from a function in time, starting from the function in time. Sometimes this f is not capitalized, like here. F not capitalized characterizes the function in time. F capitalized characterizes the transformed function. This means from a function in time, f typically not capitalized, we transform in this expression, let me say this function, is in a particular function in S, in which S, we can see here, in which S is the complex variable, which consists of a real and, or better to say, plus an imaginary part. This S is in a complex variable, is written here. This means this transformation is a transformation quite abstract, extremely abstract, because we transform something real, t, here I flesh out, I didn't put the formal definition, because I don't want to fill up the slide of many information. I try to tell you a little bit now. T is in a real variable, typically the time, something which is evolving in time. The physical representation of a phenomenon, which can be characterized by a function. The sinus of omega t is an oscillation over time, something which oscillates, a mass spring system. We will see, I don't know if the time, robota, something like that, which can be represented over time. And represented over time in our field means that we can use mathematical expression functions, which is defined over time. Again, an oscillation is characterized by, or better to say, can be represented with mathematical structure, with sine, cosine, and so on. Just to give you some feeling. Coming back to the definition, it is clear that the meaning is nevertheless complicated to be explained, because it's abstract. To transform something real in something complex, which consists also of an imaginary part. Already the word is tell us something interesting. Imaginary part, something which does not exist, but I can imagine. S equals sigma plus j omega. Do you remember math j? Root of -1. Strange. Think that mathematics, should help us to simplify some complex situation. It seems to be from this definition that we complicated the situation, because we have something real, an oscillation, which I can graph the sinus. Remember in gymnastics, I can graph the sinus, I can graph the cosinus. Now, if I transform the sinus cosinus in a structure which consists of a real plus an imaginary part, it seems to be that we cannot really interpret it in physical sense. In fact, at the end, we will see that the advantage of this approach is just a representation. We will see that this approach here allows to avoid what we learned in dynamics. What I intend. You remember, I told you how we can solve the differential equations. I insisted a lot of the differential equation method. You remember in dynamical system. Now with this method here, if, please pay attention, if the differential equation or differential equations are linear, we don't need dynamical system anymore. It's not totally true what I am telling now, because to have an idea, then a physical idea, what happens in a system using the tool of the differential equations helps in any case. But sometimes, for practical reasons, we try to avoid the solution of the differential equations. And this is in a method we will see using the transfer function to obtain a possible solution without considering the methods of the solution method of the differential equations. We will see that we will pay the price. No? We will pay the price. The differential equations, in any case, tell us something more than the transfer function, but often is enough to use the Laplace transform in order to build the transfer function to perform controller, in particular in automation and so on. This means it makes sense to tell you this part here. The price is exactly written here in red. I didn't comment at the beginning. External representation of a system is exactly this. This means using these methods, using Laplace, we will, okay, extended method allows to but in any case, directly, let me say, directly, we will consider just an external representation of the system. I will clarify a little bit better what I intend when we go in depth on the detail. Okay, this is the definition. Let me see if I forgot to say something in this introduction. Yeah, shortly. It's a linear transformation. It's a linear transformation. This means, I don't know if you remember math, linear transformation means if I have a sum of two functions, function f and g, in a combination, let me say, in a combination of two functions, we can see here, the Laplace transform of the combination of these two functions, we can see here, is basically the Laplace transform of the first function plus the Laplace transform of the second function, eventually multiply by constant. It could be also complex. It's the linearity. I can separate the contributions because the integral is in a linear operator. I think at this moment we can go ahead. Yeah, more practically. Look, let me consider some transformation or some transforms of some important signal. We can see here this signal here, delta of t. What is this function here? The name is delta impulse or Dirac impulse, or in some books, unit impulse. Is defined with these two sentences. The first sentence says that delta equals plus infinite if t equals 0, 0 if t not 0, and together with this part of the definition, that's the integral between minus infinite to infinite of delta of t equal 1. Quite complex to understand what it is. Why it's quite complex? Because for us, infinite plus infinite minus infinite doesn't mean anything. It's just a way to say. We cannot interpret it with this infinite. We say just large, more large, even more large. Not only. The particularity of this definition is infinite, large, just in one point, in an infinite small interval of time. This means it's clear, extremely abstract. Less abstract is this expression here, because this expression here fixed, let me say, if you think that the integral represents somehow the surface, if you remember in high school, fixed as the surface of this delta is finite. It seems to be nevertheless abstract, this, but now I will clarify with some pictures what I intend with this definition, and in particular with the second part of the definition. Before showing you, look at this scheme here. Just try to image does this delta impulse or the Dirac impulse. Did you hear about Dirac impulse or that? Not yet, no? It's important. Why that? Because very often in the system, we put a real impulse, not this one. This is not real. This is some ideal, because infinite does not exist. But now I will clarify better the definition. We will put an input and a real impulse in order to analyze the answer, the response of the system. Basically, as if we perturbate the system, just very shortly, but with an amplitude relative large, in order to see what happens in the system. The idea is to calculate or to analyze the impulse response. Now, let me go in depth on this mathematical definition. Look, so with this picture, we can understand. Here, we can see three possible real impulses. The ideal impulse, what I told you before, let me say, if you look at these three impulses, we can see that from this, let me say from left to right or the right to left, and from this to here, we will try to tend to an ideal impulse, which is very, very, very short in time, very, very large in amplitude. Now we can understand the definition. At t time equals 0, the amplitude is infinite. No meaning for us. Infinite for a human, no meaning. Has infinite small. We cannot conceive an infinite small interval. We cannot conceive an infinite large amplitude. But we can think about, we tend, look at these three impulses, real impulses. From here to here to here, we can see that we tend to this definition with this expression here and this one and this one. Let me analyze this. Look at the first one, at the first picture here. The amplitude is not infinite. Again, infinite for us, no meaning. This means one. It's large, but could be also large. One is much, much larger than 10 up to minus 6. It's large enough. Infinite small, infinite short is, again, with respect to, I don't know, minus 10 on 10 is much shorter. No? Anyway, we have a signal that change at time or at the point t minus 0,5 from 0 to 1 and come back to 0 at 0,5. Of course, if this is the time, it's a little bit strange to think about minus 0,5. Practically means that we have time 0 somewhere here, and then we have a point, which I called here minus 0,5, but could be also any kind of time, which I change from 0 to 1, and then after 1 second, let me say, I come back to 0. This is the meaning. What is the surface, or better to say, the integral? Huh? You remember in high school, we interpreted the integral as surface. Remember this, this is easy. This means the integral of this signal here is that there's a blue surface. Did you agree? No? Is 1 multiply 1. 1. This means this impulse at least respect this part of the definition. The integral between minus infinite to infinite of this real signal at least respect this. Did you agree? No? It's easy. 1 multiplied 1 is 1, and the surface. Of course, this part here is not respected, or at least is not partially respected, because we cannot respect this first condition. Infinite for us is not possible to be represented, it's not possible to be conceived. In particular, t equals 0, at t equals 0. This is okay. Not totally, because the interval should be, let me say, this interval should be infinite small, but anyway, it's somewhere in 0. It's somewhere in 0. But this is absolutely not possible to be respected. In general, this condition here is not respected, no? Because also 0 is just at point 0. This means it's just a rough approximation. But at least, to conclude, at least this condition here is respected. Therefore, I told you in particular is important this condition here, because states not only the ideal definition, but also the practical one. Now, move from here to here. Is it boring? It could be boring. If it's boring, I go faster. But I think you didn't see this, the concept of delta until now, or at least not in this form. It's an impulse. Impulse, you heard about impulse. In my opinion, it's important to go a little bit in depth so we can understand later again this impulse response. I will show you in the paper which we generated in the bachelor thesis, which we applied this important concept in order to motivate you to analyze together with B also at home to go in depth on this. It's in automation could be also applied. It's in the topic of more control system. I will show you the paper which we generate with Benedict and Mohammed. I don't know, Tam, you know Mohammed? Yeah, you heard about him. No, Mohammed Dihab is a student of mine. We did together a bachelor thesis on the levitation system.
Does he do simulations from in work with Kusuma now?
No. It's a student of mine. I'll show you the paper later. Okay, look at this now. Here, we shorted the interval with respect to this one, and we look here. We considered a larger amplitude. But if you do here the integral, it's again 1. Look, what about this interval here? It's 2 divided 6. Here, the integral was 1, from minus 0,5 to 0,5. How large is this interval in terms of time, let me say, is 1. How large is this here? 2 divided 6. 2 divided 6 multiplied 3 is 1. Again, the surface, this means the integral. I try to recall also your knowledge in gymnasium, in high school. This means this real impulse, I can apply this in Simulink, in practical application. I can do that with the instrumentation. I can apply this. This expression here is again respected. And we try to approximate better this part of the definition, both, because t, the interval, is smaller, and we increase the amplitude. Going ahead, I can reduce again the time in which the impulse is not 0. We can see here between minus 1 divided 20 and 1 divided 20, and I increase again the amplitude. The surface is the same. Again 1. Look, here we have, what is the amplitude here? The basis, 2 divided 20. The amplitude in which this impulse lasts takes 2 divided 20. The duration of this phenomenon, 2 divided 20 multiply 10 is again 1. Did you agree? Did you agree that the surface here, the surface here, the surface here is the same? This one. Should I have German speak? No, it's clear, no? The surface is all these three surface equals one. But let me say, roughly speaking, the structure of the signal is totally different. Totally. It's different in the sense that I reduce progressively how much will, let me say, time will take, and I increase the amplitude. In order to justify, in order to explain this abstract definition, which I called ideal impulse or the delta impulse, in order to show you that this is the most important part, which will characterize this part here, all delta, let me say. And of course, this part here is the ideal part of the definition, but theoretically means that if I am able to do, if to reduce the duration to zero, that to zero is impossible, but small enough or infinite small, mathematically we say, and increasing theoretically infinite the amplitude. In order to realize an impulse response, we takes into consideration the characteristic of the system. If the system basically is has an input, an impulse, which basically realizes as an initial condition directly without any transient, because here the system, the signal theoretically doesn't have a duration. Look, let me go ahead with this signal here, and then we will come back to the Laplace transform. I think I need a couple minutes. Exactly. Yeah. Look at this. Look at this signal here. Unit step. The unit step is defined. We can see its graphical representation. It's defined 0, let me say before 0, and 1 starting from 0 for t larger or equal 0. We can see at time 0, we have the value 1, and we remain to 1. It's in a step. Here, the representation is strange because this part here, I mean, look at the mathematical definition. Before 0 is 0. At 0, we are already in 1. At equal 0 is already in 1. Yeah. Again, here is quite abstract because also in this case, it's difficult to imagine what happens at 0. Because again, we have something which happens in an infinite small time. I mean, also here, no? If you look at this definition here, the ideal definition says that something happens between 0 minus and 0 plus. Do you know this concept here? 0 minus and 0 plus. Short before 0 means 0 minus. 0 plus means short after 0. How short? Infinite small. Infinite short in this sense. It's quite similar. We have a change between 0 minus and 0 plus. You know, understand what is 0 minus, 0 plus? Short before 0 means 0 minus. Short after 0, 0 plus. It's clear that it's quite abstract for us to understand what happens, because again, we have to do with an infinite small, let me say, interval of time. The last sentence here, we can interpret it, in my opinion, much better than this one. And then I will show you what I intend. But if we are able to interpret this sentence here, I hope that I share. Yeah. Yeah, because sometimes, yeah. If I am able to interpret this sentence here, I will show you in 1 second this here. Of course, if I apply the integral to this expression here, I will obtain this. Because the integral, let me say, is the inverse function, let me say, of the derivative, of the inverse function of the derivative. If you do the integral of this part here between minus infinite to t equals the integral of this part here between minus infinite and t, is clear that I will obtain this, because this part remains the same, the integral of minus infinite to t. And the integral of the derivative is the function calculated between minus infinite of t. But this function here, calculated at minus infinite, is 0. This means it's sigma of t. I don't know if you see this. Once I have clarified this, this is clear. If I apply the integral left and right here, clear? Should I do it? No, it is no. I try to remember that the integral is the inverse operator of the derivative. This means the integral between minus infinite and t of this expression here, which is in the derivative, is sigma calculated between minus infinite and t. But sigma calculated as minus infinite is 0, we can see from here. And at t is t. Excuse me, is sigma of t, which is 1. But in any case, it's sigma of t. Let me now clarify this expression here. Look again at our real impulse. The idea is to show you that this expression here came basically from the definition of delta, which is quite abstract. But if I consider now the real case, here I consider these two cases here. I didn't have place to draw, but from here is easy to understand. Look, again, the derivative of this function here, the sigma, should be equal delta. Ideally, it's extremely difficult to show you, but practically, yes. Look, think about this red function. Think about this red function. If you do the derivative of this red function, we have 0 in this interval here because no changes, 0 in this interval here. And what about the derivative of this linear change? Is 1 divided 1. The derivative is the rate. What is the variation of this rate? This distance divided this distance is 1. This means the derivative of this red, let me say, function is 1. This means is this level here. Or if you want, you can see here this level here. But let me show you this level. The derivative of the red line of the function, which is a real step. Here we again input step, but ideal input step. Practically, let me say, it's impossible to obtain this. What we will obtain is this one. What we will obtain is something similar to this one, and we can do the same here. Basically, the changes can be reduced as we want, the time of the changes, but cannot be exactly 0. But anyway, the derivative of this red is equal to 1. What is the derivative of this red line or the function here, which is a real step? It's 3, because it's 1, this distance, divided this distance here is 1 divided 2 divided 6. It's not clear what I try to express. Now, we can understand. The derivative of this is 1 in the interval. The derivative of this here is 3 because it's 1 divided 2 divided 6. How we can calculate the derivative of a linear changes? This divided this, no? I don't need to calculate. When I change linearly, the rate is amplitude divided this one. No? We learned it at school. How fast changes this? This distance here, 1 divided 2 divided 6, 3. Exactly the amplitude of the impulse. Therefore, we can understand that ideally, if I have something which change over time in its infinite small interval, we can say that the ideal delta equals the derivative of the ideal unit step. Again, the ideal impulse, this here, can be seen as a derivative of the ideal step. Here is a little bit the explanation if you think about this slide in terms of limits. No? If I didn't calculate here because I can do that. No? But the concept is the same. Basically, I will change in this interval here until 1, and the derivative is 10. I will change faster and faster if I reduce, for instance, this interval. And this is important because we have two possible, let me say, answers, impulse answer, as I told you, and input and step answer or step response. Okay. Shortly about the Beck Laplace transform, the definition is quite complex, we can see here. We don't use typically because once we build the table of the Laplace, we can use the same table to calculate or to come back in time. This means the inverse Laplace transform is a mathematical expression which, given the Laplace transform of a function, we can come back to the original real function, let me say. Exist, we don't have to learn, because we will see that we can avoid to calculate. Here is just again the definition. I would like to go ahead and let me do an exercise which I will calculate the Laplace transform of a step, unit step. One, do you remember? 1 if t larger or equal 0, 0 otherwise. This means before 0. Now, this symbol here is a little bit strange, but means starting from this function here, the real step, the unit step or ideal step, to Laplace of sigma, the Laplace transform or transformation of this unit step. Now, it's extremely easy. I apply the definition. You remember the integral between 0 and plus infinite of f of t, our function, which is sigma in our case, multiply this exponential function up to minus st in dt as is in parameter. At this moment, quite abstract, quite abstract. It's in a parameter. I can write this expression in this form here because before 0, it's 0. Why I put 1? Because before 0 is 0. This means I don't have to consider because the Laplace transform of 0, I didn't tell you, but is intuitive, is 0. Now we can do that. Yeah, the integral of exponential function is easy because it's the exponential function itself, but I have to divide it by minus s. I don't know if you remember the rule of the integration. You don't have to remember, but if you remember in math, the integral of this exponential function up to minus alpha t, up to minus st, as in this case, in which s is a parameter, in which alpha is a parameter, is exactly this expression here. I don't know if you remember, you don't have it to recall, but it's the integral. Calculated between 0 and plus infinity. We have a 1 divided minus s, which remain because s is a parameter. We will see in our case is a complex variable, but in the context of the integral is the parameter because the integral is in t. The calculation here is 0 minus 1. Why that? Because the exponential function with a negative exponent at minus infinite is 0. Calculated at 0 is 1. Do you remember this rule of integration? Huh? It's clear, no? What I meant. This means the Laplace transform of the ideal step, unit step, is 1 divided s. Forget the meaning. It's 1 divided s. Look at this now. If I have to calculate the Laplace transform of delta, we will see that the Laplace transform is equal to 1. I would like to skip the demonstration, the direct demonstration of this, because I think it's here. Yeah, it's quite boring, but it's here. I will give you as an exercise. Atomic exercise is already here. It's boring because I have to apply the partial integration rule. I don't want to do in the lecture. It's quite boring, belong to math. What I would like to emphasize here, why it is 1, practically, more practically, we can see in the slide. If you remember that the delta, the impulse, the ideal impulse equals the derivative of the ideal step. This, you remember, I discuss a lot about this now. Which implied this, I discussed a lot about this. No? Do you remember? Where is it? Yeah. We can see that intuitively, more practically, is 1. Because practically, this function starting from 0 is 1. Let me say it's 1. Huh? Sigma is 1. Of course, before 0 is 0. We say practically is 1 because if t is the time, what happens is already done. Huh? Starting from 0 is 1. This is a little bit the idea why the Laplace transform of delta is equal to 1. Of course, it's not a demonstration, but practically we can see in this form here. Yeah, practically the reason is that the integral of delta is equal to 1, but it's not the demonstration. No? It's not the demonstration, but the idea of the demonstration is a bit more complicated. At the end, we obtain this one. Let me a little bit go ahead and let me do one of the most important Laplace transform. Exactly. Then we will conclude with the table. What is the Laplace transform of the exponential function? First of all, before doing the calculation, why this is one of the most important Laplace transform together with delta, together with the sigma, the unit step. No? Because if you remember in dynamical systems, the exponential function, e or the exp as you want, characterizes the answer of a linear system. Do you remember the exponential function? It's always there in the linear system, in the answer or in the solution of the differential equation. Answer equals solution of the differential equation in our language. This means it makes sense to analyze this Laplace because it makes sense to analyze the output, or the answer of a system. This means I have to apply the definition. F of t now is exponential function up to alpha t. This is in the definition. Look, this expression here can be written in this form. If you remember that multiply through exponential function, I have to add the exponent. Is this difficult? No, it's math, no? From here to here is easy, no? I added the exponent. Both S and alpha are parameter. Then S, we will see that in particular, I already told you, in particular parameter or the variable, the complex variable. Now, the integral of this expression is easy math, no? Is the exponential function divided the exponent. Do you remember the rule? Calculated between 0 and plus infinite. Yeah? Did you agree these calculations? And then, again, as before, the exponential function calculated at plus infinite, or at least this exponential function, it's 0 because of this minus here. And for t equals 0 is 1. This means the Laplace transform of exponential function up to alpha t is 1 divided s minus alpha. Now, what we have seen practically in dynamical system, very often this alpha is negative if the system is, you remember, asymptotically stable. Remember this concept here. If alpha is negative, I told you in the dynamical system, typically if the system is asymptotically stable, this means we have 1 divided basically s plus at something, because alpha typically is negative, but could be also positive. We can see from this expression here that in S domain, we can characterize the stability of the system. I don't know if you remember the dynamical system. The exponent coefficients of the exponential function must be negative. This means also in S, we can characterize in the same form the stability. We say, we will see in detail later, that the poles are the solution of the denominator of the Laplace expression must be negative to have the stability. Okay, we will come back in detail on the stability concept. Look, are you tired? I would like to stop the block a little bit earlier here, because then we will see some theorems, some properties, or if you want, we can continue a little bit. But here I see in a little bit in the conclusion of this boring part in which I introduced the definition of the Laplace, and I calculated for you very quickly three signals, or Laplace of 3 signals, and the rest you don't have to calculate. We have tables, mathematicians calculated for us. Here, please pay attention. I avoided the explanation of the Laplace transform of delta is equal 1, or the explanation I try to intuitively to explain, but the mathematical demonstration is here in this slide here, but I don't want to really be boring, because here we have this partial integration. I don't know if you remember. It's extremely boring, even though easy, but extremely boring to demonstrate as the Laplace transform of delta, which is here, is equal 1. Intuitively, you can reread again this argument here. Even though it's not mathematically clarified, but it's correct what is written here. Inspired by the constant del, the derivative of sigma, unit step equal delta. But the demonstration is here. Okay, let me show you this table at least. Well, I mean, the mathematicians built this table for us. We have seen for 3 cases. For delta, even though not in detail, but it's there. For sigma, and for exponential function. Basically, we have seen the case number 1, roughly, but it's there, the exact calculation. The case number 2 in detail, and in detail, the case number 5 of the table. But of course, I can build in the table of all possible signals. Of course, must be, let me say, this Laplace must exist. Basically, the integral of the function multiply exponential function up to minus st must be fine. But this is particular. It's clear. Must be. I have to say, but of course, must be possible to be calculated. Should be possible to be calculated. Anyway, we have the tables of different function, which a mathematician calculate for us. We can see extremely important, I would like to say, the ramp. We will apply the ramp in any case. If you want, important is also sine and cosine. More important than sine and cosine is the function 11 and also the function 8. Also the function, everything is important, but what we will apply. The function 8 is important because I don't know if you remember when we have a step in a RC circuit, which we have the voltage which is going to the final value, to 1 in this case. And I don't know if you remember the dynamical system, we obtain this answer here. No? Here's its Laplace transform. Or also important the 11 and 12 because they represent the damping oscillation. We have seen this 11 and 12 as an answer of our system. We have seen dynamical system. This means also 11 and 12. You don't have to keep in mind. If you need for the calculation, the exam, I will give you the table. But just to inform you that we can transform everything which we use or which we have seen in dynamical system to be important for to analyze the behavior of a system. If you are tired, we stop here a little bit earlier. Otherwise, I try to tell you a couple of theorems which we will apply it in later. What do you think? Are you tired? If you're tired, we stop now 10-15 minutes. If no, I tell you before stopping 2 theorems, something like that. What is the feeling? I'm ready. For me, it's not boring, but it could be that for you it's boring. Okay, we stop 15 minutes, and then we will come back with 2 theorems, and then we try to do an exam exercise a little bit more practical, so we can understand better too. Okay, I put. We will see here in 15 minutes circa. See you later. Was bekannt ist ein bisschen, aber nicht in dieser Form. Jetzt, geht's ein bisschen weiter, wir machen eine ungefähre Atmung. Wir atmen ein bisschen so. Nein.
Aber die Ältere, wo möchtest du dich denn Skillset stellen? Nach Hause. Nach Hause, da ist so eine Art, die wollen, dass er so Automobil. Was? Ja, wir sind realistisch. Ja, was denn? Okay, als Nutzer ist noch ein Spiel. Das mir weil ja, ich könnte es schon als Institution verwenden. Ja, das ist aber eine Weltkonzept. Nur weil wir konstruieren, das auslesen. Nein, du weißt auch, du kannst halt konstruieren und das hat er nicht angedacht. Also, das ist Belastung. Wenn klares Sauber ist, dann nicht stabiler wird. Sowas. Das müsste halt ausrechnen durch TM und der Test sind dann halt nur umsetzen. Das ich stehe schon. Auch so, ich zuerst ein paar Feier. Nee, man kann schon nicht. Sein Kabel noch. Aber das ist überhaupt nicht so. Ja, aber das ist noch gesagt worden. Ja. Ja, stimmt, danke. Ich kann auch nicht ja. Für ein Einwand. Der kann ich mal. Lieber ein was? Achso, ja. Ja, dann war das so, weil ja, und ich habe ihm mal gesagt, genau, mir auch gesehen, so, also ich konnte nicht anschauen, also er scheint noch mal weil dann warst du da schon mal, weil es halt diese Beten sagen, ja, wie muss die so ein Jahr auf Praktikum, also die Vorpraktikum wird auch nochmal voll Hamburg, das bringt mir jetzt auf der Baustelle und das ist auch einfach. Der ganze. Wenn der andere zündelt, also ja, also wenn ich dir jetzt aus dem Punkt würde, würdest du jetzt nicht erzählen, was nach der Lösung. Doch, also ich schon, ich muss noch ganz genau die Option bauen. Also wenn ich das noch nicht muss, ich noch mal anschauen, so, aber habe ich da auch schon gearbeitet. Was ich so, ich wusste nicht, das Level ist, aber angefangen, so was ist denn der und ich kann nicht mehr in das ja, ist alles gut. Das ist so Gatekeeping, das ist einfach so ein Aufwand, so wie 25 Jahre oder so, was einfach weil wir uns brauchen. Ja, gut, wenn du das anfängst, dass du auch nicht immer Aber ja, aber da brauchst du natürlich Ja, aber 20, das macht ja, das ist ja auch. Da muss das jetzt ja. Der 20 ist okay. Aber bei 20 ist, als man auch was durfte, dann kannst du immer nur das war am Anfang. Aber der kann natürlich schwierig sein, wenn du das Deutsch oder so. Ja, oder 20 Zentimeter. Vor allem, man gesagt, dann macht man dann ein. Ach so, machst du? Ja. Wenn man es halt nicht mehr. Alles ist in Hannover ist komplett frei. Kannst du jedes Modul so wie du möchtest. Achso, da wurde Praktika. Ja, ja, vor allem, weil sie haben die Studienarbeit abgeschafft. Sonst muss man im dritten Semester Praktikum eine Studienarbeit machen, der eigentlich eine Masterarbeit ist. Das ist eine Bachelorarbeit. Und das kannst du etwas setzen für die Schule, die sind so irgendwas anderes. Und das ist richtig geil. Das haben wir auch. Doch, du musst eine Masterarbeit natürlich schreiben, aber vorher war die Kritik nur Studienarbeit schreiben und Masterarbeit. Und das ist so quasi zweimal eine Abschluss ab. Das ist ja halt sinnlos zweimal hintereinander. Aber wenn du das dann mit Modulen aufhören kannst. Bei denen auch noch? Ja, genau, das ist das schon. Wir können ja mal nächstes Semester abwarten. Jedes Mal meine Chips bekommen, der kommt was Hallo, dann habe ich an. Nein, aber das ist nur gesagt. Ja, du musst 15 P nachholen. Oder mich als Honig oder Brot. 15 P? Aber hat der den Weiß? Ja, verschiedene. Ja, das ist halt ein Ziel. Aber es nur voraussetzen. Ja, aber Maschine hat ah gut, er geht nicht hin. So, meine Mutter hat ja nicht gut, ich so letztlich so. Wir kommen hin, alles klar, nur noch 3 Tage. So, okay. Das gibt es auch. Da haben wir schon Proben. Ja, aber so, es hat viele Leute, die haben nicht gemacht, das ist cool. Ich mache eigentlich am Tag. Augenargument von Angebot des Geistes. Ja, der irgendwie 4 Kategorien und es werden mal 4 Hauptinhalte von Input an Baby und Nachweisung. So, geht der Vorstand. Aber Ihnen ist super. Hallo. Ich glaube, die freuen sich da, wenn sie den Skandal haben.
war schon noch im Alter schon öfter. Das ist langweilig. Der spielt schon mit irgendwie Film.
So historienmäßig oder so?
Das ist zum Zeit auch. Wir haben das so eine Arbeit schreibt und so.
Ja.
Das macht das Arbeit schreibt und so. Der schreibt zum Teil dann noch über niemanden.
Ich sage auch, studieren ist das neue Arbeit. Jeder Tanzlehrer und alle Tanzlehrer und Tanzschule machen alle nochmal BWL studieren.
Aber sonst können halt nicht wachsen.
Ich bin hier jetzt weg, also er hat ja nichts.
Ich meine, das kann auch denken, ne? Ja, und meine Hand viel Spaß.
Aber auf den Linsen, der nennt noch nicht sehr.
Ja, ein Arbeitsbärchen. So das Ding ist, ja. Mein Vater kommt dann weiß. Weiß nicht. Und dann fragt der diese. Also ich schon
Ja, oh, einfach nur wegen dem Vater, ich weiß nicht.
aber ich mache das halt auch absolut auch machen. Das hat ja das heißt so warm und das was das ja da kann auch sein, dass er nochmal heute so aber jemand damit vergisst, dass er Valerie, weil ich begleite dich. Also kurz diese Tabelle mal aufzunehmen. Vielleicht da.
Vielleicht Silvester nicht nur noch mal erlebt haben.
Dann würdest du Report haben.
Man kann das
Aber sofort bin ich gestartet mit der Uni. Kein Auslandssemester. Weil die sind da ist ja auch nicht. Das ist
kein Fleisch,
aber die Frau ist WG machen. Aber diese Frau ist nicht manchmal krass, dass wir haben so Bedingungen. Okay, weil wir sind fein mit, ja, wenn du aufhörst zu studieren, dann hör ich auf zu arbeiten. Bei meinem Mitbewohner ist es so, wenn du aufhörst zu studieren oder fertig bist zu studieren, dann trenne ich mich von meinem Ex-Freund. So, das ist voraus.
Also meine Eltern haben auch so ja nicht sehr heraus. Das kann man ja sagen, dass ich einfach die Durchsage der das fertig ist. Aber ich habe gesagt, das war fest, weil ich vor das Produkt gemacht. Und das hat mir gesagt, weil er war. Und dann fest und ich hatte dann nochmal angefangen, es war so, das man hat sich da ja wirklich bis die ganze Zeit so ein Produkt zu nehmen. Weil es meistens ja ist, alles wieder eine Fantasie.
Hast du ja auch gesagt, was hast du?
Ja,
Ja, dann ist ja, muss ich nicht mehr sagen. Ist ja schon. Das ist wahr.
es ist aber für irgendwie habe ich es sagen, über die beiden Fuß.
Ja, das ist. Oh, halb.
Ich meine, das ist halt das Zentrum und alles in einem bisschen.
Ja.
Ja. Aber ich kann ja eigentlich. Das ist
Das ist halt welcher Bruder.
also noch ein bisschen weniger.
Der kannst ja aber anschauen.
Ja, ich habe auch in den Krankengeld genommen. Das ist ja bei uns ja auch total überwachsen. Leider wieder auch nicht über.
Okay, das haben wir jetzt auch. Lass noch sehr schön. Das sind also nicht richtig. Ja, rotes Element. Der Ding ist anscheinend. Ja, das dachte ich auch, aber ich glaube, wenn ich dann durch 1, 2, 8, sonst was kombiniert. Ja, wie gesagt. Das und letzten Endes möchte ich ja diese Einlegungstechnik haben hier kombiniert zum Beispiel. Ja, Sachen dachte ich auch, dass sie eher eine Automation gibt. Ich weiß nicht, wie es dort zustande gekommen ist.
Wo wäre mein Sohn?
Nur auf Konstruktionsweise. Wir machen halt so Projekte. Das ist eigentlich auch.
Aber ich habe mit meinem Mann gesprochen und er meinte, also, ich habe das eben auch, er meinte, ich kann auch Baustart. Ja.
Ja, ja, die werden doch die erste Hälfte ist, als das einfach TM1 machen. Und dann bin ich selber auch nicht so und so fort.
Und er meinte, wenn ich so alt bin, das auch gut. Ich meine, das macht er dann besser, zu machen,
Ja. Und es ist keine Frage, es ist übelst Verbot. Das ist jetzt das nur einmal Vorteil, das ist eines anderes. Aber es geht ja erstmal um, ob du drin bist. Und das ist halt bei manchen schwierig, die sagen, CCP maximal, du darfst nichts nachholen vorher. Du kannst mit 20 CP kommen, die kannst du nachmachen. Das ist schon mal sagen, du als Net. Und sonst die wird.
Und dann kommt man einfach, wenn man der Schau entscheiden ist, dann wieder machen, dann ist es ja.
Ja.
Vedi l'evidenza. Okay. Waren wir hier? Theorem 2, Theorem 1. Okay. Let me restart from here. About these properties, I will come back when we will use with the exercise. At this moment, I don't want to go more in depth about this convolution product and so on. We can skip, but very important now on a couple of theorems which can help also directly today, I would like to say, or indirectly. Look at theorem number 1. The theorem number 1 is a nice property. Theorem is its own property, which basically says to us, or tries to realize a connection between the derivative of a function and let me say its Laplace transform. Why this is important? Because if you remember the differential equations, a differential equation is a connection between derivatives. Remember, x dot dot plus x dot plus x equals 0. This means this theorem here try to give us the possibility to transform at the end of the differential equation in Laplace domain. Extremely important, this concept here. Extremely important. The theorem allows us to transform the differential equation into S domain. We will see exactly now the advantage of this approach, or the general approach in terms of Laplace. Look at this theorem 1. The theorem I sketched is not exactly mathematically is correct what you can read, but of course I avoided this symbolism notation. I tried to simplify the notation. We have the function f2 of t, the function of time, equals the derivative of f1 of time. This means we have the function its derivative. The function is f1 if you want, and its derivative is f2. Or vice versa, if 2 equals the derivative of 1 with respect to t, and please pay attention, this is quite important, at least in this formulation. If 1 of 0 equals 0. Again, I have a function f1 and its derivative. Assuming that f1 at time 0 is equal to 0. We will see, I don't know if we have so exercise, but we will see that we can also consider more general case in which f1 of 0 is not necessarily 0. But let me tell you about this basic form. Then, let me say conclusion of what happens, roughly speaking, is the Laplace transform of f2 equals s times Laplace transform of f1. Or with other notation, f2 capitalize of s, capitalize means in our notation, just the notation aspect, is the function in S domain. In fact, we can see directly from here. F2 in S domain equals S multiply F1 in S domain. It's extremely important. Now I have also the demonstration here. It's just one line. I have the demonstration. I don't want also go more in depth because again, it's this partial integration. I don't know if you remember, it's quite boring. It's quite boring. I don't know if you remember, but I can sketch a little bit. I can sketch a little bit. Is two line, but more than insisting on the demonstration, I would like to emphasize the meaning, the importance of the theorem. Of course, if f1 of 0 is not 0, we have here something more. We have here something more. It's also possible. It's also possible. I mean, the theorem. We have another version of the theorem. In case f1 of 0 is not 0. But let me remain on this basic here. It is the most used, at least for our case. But the meaning of this theorem is exactly what I told you before. I can transform according to the theorem. I can calculate the Laplace transform of a derivative of a function. If 2 is the derivative of a function is 1, f1, excuse me, f2 is the derivative of the function f1. The Laplace transform of f2 equals s multiplied the Laplace transform of f1. This means I can transform a differential equation using this theorem here, just thinking that the second derivative of f1, the Laplace transform of the second derivative of f1, we can demonstrate, but intuitively we can understand just plugging in, if you want, is s squared multiply f1 of s. The derivative, the third derivative of f1, f1 derivative 3 times, is s up to 3 multiply f1 capitalized of s. Just to plug it in, or to repeat, to reapply again the theory. I would like to skip this demonstration here. Is basically the idea is this partial integration. Probably Benedict told you about the partial integration. It's a math exercise. I don't want to repeat it here. It's nevertheless used to demonstrate exactly that the Laplace transform of a derivative of a function is time the Laplace transform of the function. Very important to notice here that here applied the concept that f1 of 0 is 0. We can see from here. If not the case, I will have here minus f1 of 0. Change a little bit. Yeah, I have some exercises, some aspect probably can be seen together. Yeah, I also here some aspect which we can discuss together when f1 of 0 is not 0. This is the basic form of the theorem. Again, at the end, what we have to have in mind that I can calculate the Laplace transform of the first derivative, I can calculate the Laplace transform of the second derivative, I can calculate the Laplace transform of derivative up to n, just reapply this theorem. Again, example, the second derivative of f1 in Laplace domain is s up to 2 Laplace transform of f1 of s. Again, if s1 of t is not 0, we have here minus f1 of 0. We will see I have an exercise in which we can apply this more general version of the theorem. is related to the initial conditions of the system. You remember dynamical system, in a differential equation, we have always an initial condition. Derivative of f1 equals something with f1 of 0 equals 0 is different if f1 of 0 equal, I don't know, 1 over 2. But this is possible to be applied. The difference is here we have a minus f1 of 0 because remain from here. No? What is this calculation here? Independently, don't learn this one, but believe me, it's correct. I copied from a book. I trusted the book. Here we have f1 of 0 minus 0 because the exponential function up t infinite plus infinite because of this minus is 0. Remains here minus f1 of 0. We will see an exercise, what is the minimums. Theorem number 2. The theorem number 2 is just 2 words, I would like to say. Now, I told you about the derivative theorem. Now is the integral. We can understand with the similar form, with the similar condition. If I have to calculate the Laplace transform of the integral of a function, it's intuitive to understand that f2, this is the integral of f1, its Laplace transform equals 1 divided s multiply f1 capitalized of s. It's intuitive. The demonstration is also a little bit boring because again, this partial integral form or method, but is intuitive. If this is s multiply f1, f2 of s equals s multiply f1, is clear. In case of integral, f2 of s is 1 divided s. This means the derivative characterized by the multiplication by s, to sum up. The integral is characterized by divided by s. Recall a little bit the rule of the integration and the rule of the derivative. Do you remember the derivative of a function, of an exponential function, for instance, is the coefficients multiply the exponential function. You remember here, multiply the exponential function. The integral is the exponential function divided the coefficient. Why I reflect this? Because the Laplace is related to the exponential function. Exponential up to minus s multiply t. I don't know if it's clear what I try to intend to tell you intuitively. Why is 1 divided s the Laplace transform of the integral? And why is s multiply the Laplace transform in case of the derivative? Again, here, if f1 of 0 is not 0, I have something which I have to subtract. No? Let me see if I forgot to say something. Excuse, in this case, I have to add. If f1 of 0 is not 0, I have to add plus f1 of 0. Let me see if I can confirm. Yes. Let me see what I can see. Okay, this I told you. This I told you. Right. I think I didn't forget anything. Mhm. Okay. Okay, okay. I think I didn't forget anything. Final value theorem. This we will apply also this one. The theorem says if I want to calculate the limit of the function f of t for t toward infinite, this equals limit of s to 0 of s multiply f of s. Or equivalently, very often we consider not a notation because it's used for errors in a control loop. The limit of the error of t for t towards infinite equals limit of s to 0 of s which multiply e error in this case, instead of f is just to change the notation, e capitalized of s. The demonstration is extremely easy, just to apply again the theorem directly, let me say, the definition of what? Of the derivative of a function. Because the idea is to show you that we have a multiplication of s, and the multiplication of s recalls us the theorem of the derivative. This means if I want to calculate now the limit of s equals 0 of what? Of the Laplace transform of f derivative is here. No? This part here is the Laplace transform of f derivative. Then I can include the limit inside because the integral is calculated in time and s is just in a parameter. This means this equal this one, which basically means exactly this expression here, because for s equals 0, the exponent function of a exponent up to minus st is 1. That means I can write everything in this form here, in which instead of infinite, I write in different form. Yeah, and basically it's exactly what we want, because the integral of the derivative is the function itself, limit of f of t for t toward infinite equals limit of s of f of s for s equals 0. The reason is that the Laplace transform of the derivative is s of f of s, as we have seen before. No? We know that the Laplace transform of f derivative multiply the Laplace transform of f of s of the Laplace transform of derivative of f of t, excuse me, is more easy to show you directly than to express. Extremely important, because very often it's easy to calculate the limit for a variable to a point in particular 0 than the limit to infinite. But the reason is again the main advantage that we transform everything which we had in form of differential equations in form of algebraic equations. Initial value. The initial value is quite similar. It's a theorem which states how we can calculate now the limit of a function, or in this case of an error. In the control loop, we will see what I am changing the variable later. For t to 0, 0 plus means short now after 0. No? Let me say, roughly speaking, 0. Which is basically is a little bit in a dual form of the final value theorem. No? We can see with respect to this one, I will interchange just the limit, if you want. Here, for t to infinite becomes s to 0. Here does not change the structure, but I will change let me say, the limit. We can see here before we had infinite, t to infinite, now we have 0. Here before we had 0, now we have infinite. The demonstration is similar as before. Again, in this case, applies the Laplace transform to f, in this case directly. If you want, you can look about demonstration is in the exercise of Mate 1, I think, something like that. Yeah, let me tell you just shortly about this slide here. Yes, excuse me, I put here 2 times S description. I have to correct, but it's not. In order to introduce the concept of the transfer function, which we will use now in exercises. In order to introduce the concept of the Laplace or the transfer function, in terms of Laplace, but typically when you speak about transfer function, it's Laplace. I would like directly now discuss this sentence here. G of S transfer function equals Y of S divided U of S. We came nevertheless from the concept of the convolution product. You remember I told you I skipped this part here. Probably I can come back very shortly to tell you a little bit more in depth now. But let me fix now the idea, and then I tell you about this convolution product very shortly. But in particular, the idea is to fix the concept of the transfer function. We can see here the transfer function G of S, we will do now with some exercises, is in a relation between what? Between, if you look a little bit in this notation, if Y, as I told you in the dynamical system, is an output of the system, Y of t, is the ratio between Y capitalized of S. This means the Laplace transform of the output divided the Laplace transform of the input. U of S is typically the input. We can see, if you recall the lecture of the dynamical system, we can see exactly the same notation. Y of t, or possible notation. Y of t is the output. This means Y of S is the Laplace transform of the output. U of t is the input. U capitalized of S is the Laplace transform of the input. This means, roughly speaking, not only roughly speaking, also in a possible definition, the transfer function of a system, because we have an input of a system, we have an output of a system, is this ratio. Output transform divided input transform. Now, a little bit more in depth, but just roughly speaking. If you remember, I skipped this property here in the middle of the slide, Yes, the linearity, I told you quickly, because of the integral, we can consider the linearity also of the Laplace transform because it's based of an integral, and a parametric integral of an integral. Look at this in the middle of the slide. It seems to be abstract, but it's not so extremely abstract. The convolution product between two signals are defined in this form here. It's a little bit abstract. I have another presentation, something more in detail about this convolution of a product, or this convolution of two signals, which is in the product, in a particular product, is indicated, let me say, in this form here, is an energetical product. We can demonstrate that this product defined in this form here, the integral is in tau, no? The integral is in form of tau, basically between the function f of tau and an input u, which is, I don't know if you remember in math, translated in tau, in time. inverted and translated in time. The variable is tau. F and U domain in this context here is tau. Basically, it's in the product between F, the inverted in which sense? Inverted in time and translated. It's quite abstract. If it could be that I can show you something more about this product here. It's used in signal processing very often to calculate the interaction, let me say, between the signal which belong to the receiver and the signal which arrive to the receiver. F is belong to the receiver, U is the signal which is transmitted. Anyway, the integral is in tau. We can demonstrate, the demonstration is not here, but I have it, that the Laplace transform of this convolution product between f of t and u of t, it's basically the product between the Laplace transform of f and the Laplace transform of u. Why this is nevertheless important for our transfer function? Let me come back to this slide here. And look here. As I told you, U is named. In this context here, U is named. Now, look here. If the input is the delta of t, if U here is the delta of t, do you remember the Laplace transform of delta function is 1? This means that the transfer function is exactly the Laplace transform of the output. I don't know if it's easy from here to see, no? I hope it's easy. If U of S is equal 1, this means U of t is delta of t, The transfer function related to the input delta of t is directly the Laplace transform of the output. We say that y of t is the impulse answer. This means the Laplace transform of the impulse answer is the transfer function. This is at the end. If you want to characterize within one word or one sentence the transfer function, the transfer function of a system is the Laplace transform of the output of the impulse in input, of the impulse response, if you want. Laplace transform of the impulse response. The transfer function, the Laplace transform of the impulse. Let me see what I can add here. Yeah, I think we can consider an exercise. Let me see if I have this exercise more explicitly in. I can use also this material here. Or let me see if I have something more detailed in the slide. Let me see. You realize that the exercise is not so complex. Let me see if I find it. I'm looking for you. It could be. Okay, if you look in. Found it. Let me see. I have something. I have something. Let me see. Yeah, I think it's nice. I hope it's not so difficult. Let me show you this. And then I will upload. This is, I will consider this because it's more detailed. Okay, you have also this one, but I think we can go more in depth. Okay, using this slide, and I will upload everything, or you can look in YouTube as you want. Yes, I don't know when we will be ready the channel, but in any case before Christmas. But I will upload also the material in my study. No? Let me now switch on the lateral camera. Here we have a similar, or I think it's the same. It's the same. Why doesn't work? It's the same exercise, but in the slide, of course, I don't have much plays, and this means I didn't write many aspects, or in any case the analysis is a little bit more compact. 1 second, I don't know why it doesn't work. Oh, now it seems to be recognized. Right. Here we have a more, let me say, interesting aspect, or in any case, I try to clarify something more. At the beginning, I repeated the Laplace transform of an exponential function, because as I told you, the exponential function is one of the most important functions in general, but in particular if we have to do with linear systems. It's just a repetition, because we will use later. I will come back on this calculation here a little bit later. Let me see if I have something to write. I hope. In the meantime, I tell you about this slide. We can see that nevertheless, with respect to the table, which you can find in the lecture, here I emphasized the presence of a sigma. I don't know if it's visible, the presence of a sigma. In the table, we don't have a sigma, because basically, this expression here equals this expression here inside the integral, because sigma before 0 is 0. The integral is defined starting from 0. This means what is written here is correct at the beginning. Because sigma before 0 is 0. This means the integral between 0 and plus infinite is not sensible to sigma. I don't know if it's clear on this. It's a formal thing. But why I emphasize this? I emphasize because for the mathematician it's not so important, because this expression here is equal to this one. I don't know, Tamo, if it's clear. Sigma before 0 is 0. This means if the integral is defined between 0 plus infinite, I can omit this. I mean, I can put 1 directly. Because what happens before 0, the Laplace does not consider. Forget. Because Laplace is the way to represent in a particular form signal in time. This means what is in the past, at least in this definition. But why for us is important? Please pay attention here, because this sigma, I forgot to say before, this sigma states switch. Sigma, we can see from this picture here. I need my sigma states exactly that at time 0 we have a switch which closes the circuit if we have a circuit. If we have a mechanical system, states when everything starts. This means the model of a switch is sigma. Typically in electrotechnic, we use this notation here. At time 0, I close the switch. States the difference between 0 minus and 0 plus. You understand 0 minus, 0 plus, what I intend? Short before I switch or I close this circuit, short after 0 plus. 0 plus is short after, 0 minus is short before. Is the model of a switch is exactly the sigma. Or better to say, how I can represent how I can represent in a switch. Here is, I think we can see somehow very well. We have here a generator, also here in a generator. Here in a generator, an exponential generator could be. If you look at the circuit from this and this terminal, what happens here is exponential function or the u function, but multiplied by sigma. I mean, here is a totally abstract input function, like here. It doesn't matter. Here is in a particular input function, an exponential function. Could be in a constant, could be, we will see in the example, we can see here 1 volt. 1 volt. But from here to here, or better to say on the right, we have a 1 volt multiply sigma. I don't know if it's clear this, because sigma say when this happens. If I write sigma, please pay attention, parenthesis t minus 1, parenthesis, and I will ask you, when I will start to control, to observe, to simulate, at time equal 1. I don't know if it's clear. Sigma, parenthesis, t minus 1, parenthesis. This means until 1 minus does not happen anything. At 1 minus, I switch. Or if you don't like 1 minus, at 1 I switch. Okay, I don't know if this notation is clear. In the table, really should be, I have to add sigma everywhere. But anyway, the table was built by mathematician. For the mathematician, yeah, the sigma is not so relevant as in our case. Okay, let me do the exercise. Please, here I will consider an initial condition at this moment. We will see later without this initial condition what happens. The input is 1 volt. The idea is to calculate, the input means to calculate UC of t. Easy example. Yeah, I put some to remember this, no? The theorem 1 or the derivative theorem, in some books is derivative theorem. The derivative of f1 with respect to the time, or the Laplace of the derivative of camp with respect to the time, if, or n, f1 of 0 equals 0, is this one. You remember, s multiply f1 of this. Okay. This means the Laplace transform of UC derivative, we will see why I am considering UC derivative, but it's clear if you remember electrotechnic, if you remember dynamical system, is S multiply UC of S minus, you remember I told you I have to subtract this initial condition. If you don't have, it's 0, otherwise here I put 2. No? In general, I presented the theorem in this form. No? But I told you that if it's not 0, I have to subtract. You remember this? I told you. I have to subtract. Why is so important? This theorem now we can understand. If you remember, the Kirchhoff balance of this circuit here, starting at time 0 when, or 0 plus, if you don't like 0 again, when I close the switch, is, I don't know if I am now writing too fast everything, but is U input of T multiply sigma, this signal here, which is basically here with the sigma, equals I don't know if you recognize this expression here, which basically we have on the right part. Should I justify why this expression here? If you want, I can do. No? Is the Kirchhoff balance in this circuit here. Too difficult? It's not so difficult. I try to explain. If it's not clear, I try to calculate. The voltage between here and here is U input multiply sigma. Because we have this element here. Of course, starting from 0 plus sigma equal 1. But formally, it's exactly so. This means this balance, this expression here is valid also before 0. Also at 0 minus. Equals what? This voltage here. This voltage here, which is here, plus this voltage here. Did you agree? Kirchhoff. Or if you like, this voltage here equals this voltage here plus this voltage here. A Kirchhoff balance. Should I write? No, we can understand. This means UC is here. This should be the voltage here. Why the voltage here, this form here? It's easy. Electrotechnic. Because the current here is C time the derivative of UC. The definition of the capacitance, how the capacitance react to voltage and current, roughly speaking. But the voltage here is R multiply the current. In dynamical system, we have seen a little bit more in more complex form, state variables, energy, do you remember? In dynamical system, I introduced this balance in more complex form. More complex, not, but a little bit with different point of view. It is difficult to see this balance. Should I write? If you want, I reconsider the notation of dynamical systems, but it's more complex, a little bit more tricky. I try to repeat. If it's not clear, I write for you. Kirchhoff balance. In order to build the model, that's I told you also in the dynamical system. Here, I would like to tell you about the way to proceed in electrotechnic form because it's a little bit more easy. I don't need here to explicit the derivative. Do you remember in the dynamical system I told you always the derivative of the state equals something, equal this and function of the state and the input. and I clarified why I need in dynamical systems this form. In electrotechnique, we need a balance. And here we need a balance because at the end we want to calculate the transfer function, we want to calculate directly the answer. Kirchhoff balance. What is the voltage here? It's U input multiply sigma. This is valid at each time. U input multiply sigma. Clear, for t larger than 0 is U input, because already close. Equals what? Equals the voltage on the capacitor, or on the resistor, let me say, plus the voltage of the capacitor. Now we have 3 voltage. The input, the voltage on the resistance, and the voltage on the capacitor. This means the voltage on the input equals the voltage on the resistance plus the voltage on the capacitor. What is the voltage on the capacitor? It's exactly UC in accordance, UC of T in accordance of the notation, which you can find, excuse me, here. What is the voltage on R? It's the current multiply R, Ohm law. And what is the current? C times the derivative of the derivative of the voltage in the capacitor, you see. Therefore, we have this. C multiplied the derivative of UC is the current, in accordance with the definition of the current in the capacitor. We have just one current. Multiply R is the voltage on R. Should I do analytically? I don't think so. It's clear that the Kirchhoff law. Now, if I apply the Laplace on the left and on the right of this equality, Kirchhoff is in principle conservation of energy somehow, which is expressed in the volt balance, but it's the conservation of energy. If you do the Laplace transform on the right, and I write equals on the Laplace transform on the left, I will transform the differential equation. Look, inside the parentheses, we have the differential equation, which we have seen in the dynamical system. Now, using the theorem, I will have, what is the Laplace transform of 1 multiply sigma of t? You remember, U input is 1. If it's 10, it's 10. Otherwise, is what is this? Is 1 divided S. If I have a voltage 10, I have here 10 divided S. Because the Laplace transform is the linear transform. This means if I multiply, I told you at the beginning of the lecture today, if I multiply by a constant, the function, I have to multiply by a constant the Laplace transform. 1 divided S. If I have a 10, it's 10 divided S. It's linear in this sense. I told you, it's a linear transformation. Equals what I have in the right part. What I have in the right part? I have the transformation of the derivative, which is S time U capitalize of C, of U capitalize UC of S, multiply R multiply C, because it's linear. RC remains, let me say it's on this form. Plus UC of S, which is Laplace of UC of T. And if UC of 0 is not 0, I have to put this. We have seen the theorem in its more easy form with the UC of 0 equals 0. In our case, it's not 0. But I told you when I explained the theorem, which is not 0, I will put minus F1 of 0. Now, F1 of 0 is also multiplied by RC. Is multiplied by, I have to transform R multiply C multiply the derivative of UC. Which in the basic form is this one, but I have to subtract RC multiply UC of 0. If it's too difficult, consider UC equals 0, as I told you at the beginning in the basic form of the theory. But I already told you if the initial condition is not 0, I have to put it. At this moment, you can also consider UC of 0 equals 0. This means no initial condition in the capacitor. Could be. It's the easy form. Look, from this expression to this expression, no problems, because I did just, yeah, I put in evidence UC of S, yeah? Between this and this. Too difficult? No. Between this and this, I put in evidence UC of S. Easy, no? Again, if you are disturbed by this, consider UC of 0, no initial condition. But why I am considering? Because you attended my class in dynamical system, yeah? Everybody. You remember I insist a lot of a free answer, forced answer. You remember this was the course. This initial condition reflects the presence of the free answer. Why that? Because reflects the initial condition of the capacitor. I don't remember this. I insist a lot, initial condition, free answer, without initial condition 0, forced answer. Do you remember this? Therefore, I try to introduce. But if you don't like at the beginning, we will introduce later. Consider here 0. But if you 0, of course, we don't have the free answer. No? I'm just a force. Because now we can understand the meaning of this F1 of 0 equals 0. It's exactly the initial condition. But anyway, is it difficult to understand until here, with or without UC of 0? It's not difficult. Very important, the theorem 1 in its basic form, F1 equals 0, and or in the advanced form in which F1 of 0 is not 0. It's not in this, it's not in the presentation, but I told you if it's not 0, I have to subtract. I show you mathematical. Look, it's too heavy, too difficult that we now the lecture. This second part. It's in the consequence what I told you in the first part of the lecture, but of course it's really it's new. Nevertheless, it's new what I am telling you. Must be a little bit new because of the way. Look here now. What I did now, if until here is clear, from here to here, just an algebraic manipulation of the balance in S. And probably S is a little bit confusing. Think of the parameter, forget it's complex. Think of something abstract which cannot be interpreted. It's not wrong what I am saying, because really it's difficult to be interpreted as. Because it's not in time, it's not real. If it's not in time, it's not in our phenomenology. We are living in time. This means if the phenomenon is not in time, if the phenomenon is transformed, it's clear this is extremely abstract. But we want to do that because we simplified a lot the calculation. I show you why. Until here was clear. Now, from here to here is also relatively easy because I just manipulate this expression, but in a particular form. Look, I explicit UC of S, basically this variable here, as a function of all the rest. Why that? Because the idea is to analyze what happens in the system when we have here in a constant 1 volts, could be 10 volts. I told you has the difference. And we have an RC circuit. What happens in circuit here means, first of all, what happens in U of C of t, because U C of t is the state of the system. When we have U C of t, I have everything. Because the current is, you remember, C time, C must be given, or we can identify it, Kalman filter, or whatever kind of identification system. The current is C time, the derivative of UC. This means UC is the most important variable, the state variable, energetically reflect directly the energy which you have in the system and so on. It's the store variable. But clear, here, it's something quite abstract because it's in S, it's not in time. It's not in time. But the advantage, we skipped the differential equation. Look, UC of S from this expression here is exactly this expression here. Please pay attention. If UC of 0 is 0, we don't have this. At the beginning, assuming that UC of 0 is equal to 0. as in the original theorem form. This means we have U input of S, could be also 10, could be also 1. If it's 1, it's directly 1. Let me see, probably I have an error. Yeah, this is not exactly, it's not wrong. Let me do a small correction. Here I consider already 1. Let me see, because I don't like this form here. I don't like much. Yeah, I would like to be a little bit more precise. This means here I have to consider 1 as here. Excuse me for this error. Is 1. I don't know if some student asked me something. Why this one? Because you input equal 1. But you input multiply sigma, the Laplace transform is 1 divided S because of the presence of the sigma here. Let me clarify this a little bit better. Let me put this comment here. Even though it's, yeah. Let me, it's already here, but it's 1 multiply sigma. The Laplace transform of sigma is 1 divided S. Multiply, if I multiply U input, multiply this, I have to consider also U input, for instance, a constant, I have to multiply by 1. Now it's okay. In which we can see the this structure here, which represent the corresponding fourth answer, because we have the input 1 multiplied by sigma. And here, if you consider the value of UOC not 0, we have the free answer in terms, of course, of S. Now, using the table, this form here is clear what I'm doing. I am putting in evidence error of C in the denominator, and basically I can write this expression here in this form. I don't know if we can see what of this part here equal exact this. Why I'm writing this form here? Because now we can use the table to calculate the forced and the free answer. Why that? Let me consider without this. If you write this expression here in this form here, it's clear that if I look at the table, the back transformation, basically coming back in time of this quite abstract expression, is this one. I will show you why. It could be that I am using already directly R multiplied C equal 1. And we have here 1. Did you agree that this expression here is equal to this one? Yeah. If I multiply by RC numerator and denominator, I will obtain this. Now, Assuming that R multiplies C equal 1, just an example, in order to simplify the calculation. Here we have S, which multiply parentheses S plus 1. It's a little bit yeah. Really have to multiply here by 1 divided RC. I will do it, but before doing, let me show you why I have this using the table. Yeah, using the table in which we don't have sigma in the table. Please pay attention, we don't have sigma in the table. The case which I use is this one. Here is not A, but S. A divided S plus A. Yeah, I copy from a book, but here cannot be A plus A. No? It's S plus A. A divided S plus A is exactly in our case. In our case, we have A is 1 divided RC, and we have exactly this form. Here we didn't have multiply sigma because the mathematician didn't put sigma in the function, but we have in the switching. This means we have to consider sigma. This means 1 minus exponential function up towards minus 1 divided RC in accordance with this transformation from FT to FS, but we can be used also as a back transformation from FS to FT. This means in our case, A is 1 divided RC. Here, please pay attention. I would like to correct, but it is not easy because it's in a picture. This table is not generated by LaTeX. This is imported, but here is S plus A. A in our case, R multiplies C. 1 divided R multiplies C. We can see. This means we have this expression. It's in the fourth answer. Let me show you again in order to. Yeah. If A is 1 divided RC, it is S, S plus A. Please consider this. Is exactly what I applied. As in the fourth answer, because we didn't consider the initial condition. Now, what about this expression here? It is quite similar as before, because now we have to consider this S here, which cancel with this. If you do the calculation here, let me check again the calculation. I hope it's correct. Let me check again. Yeah. Basically, I express here UC of S equal, let me see. No. Seems to be correct. And look at the table now. Look at the table. We have that if you put here in evidence RC, in this case, we will cancel. Therefore, we have this expression. And this is the back transformation of this expression is exponential function up to minus 1 divided RC multiply sigma if you look at the table. Please pay attention, sigma is not included in the table because the mathematician, they don't have to do such kind of, it's just a formal thing, but I would like to consider. Multiply the initial condition. This means we can see the free answer also in this expression. Let me think about one thing more. Why this is plus and you have a minus? Because I bring this on the other part. No? I mean, is UC of S equals, if this bring on the other part, and then you divide, we have this plus, it's clear, no? Try to do at home. I have something more precise in the page number 2, excuse me, I realized just now. It's the same calculations, but probably some students, do you remember, ask me about, you remember the Kirchhoff balance at the end, some students ask me more calculation details, which do you remember I told you I have the possibility to write exactly the Kirchhoff balance, R multiply I is C multiply the derivative of UC. Do you remember I told you I can do it? I forgot that I had in the back page. It's exactly what I told you with words more in detail with the Kirchhoff balance, and then I put here the definition of the definition, the behavior of the capacitors, the current in the capacitor. We have just one current, and then from here to here, from here to here we have the Laplace. Then I am considering that the current E at this expression here, if you want more in general, is the Laplace transform of the current I not capitalized of T, E capitalized of T, and then I can use basically the same consideration. I don't remember exactly what I in which sequence I expressed at that time, but it's exactly the idea to do something more explicitly at the end. Nevertheless, we have this expression here is more precise because we don't have U input, we have one, and must be one. I corrected in the last part. And then with some manipulation, I will obtain exactly what I told you until now. And then we have, this is the corresponding fourth answer, is the corresponding free answer. If the initial condition equals 0, we have directly the fourth answer. Too difficult? No, I think it's, let me now show you the end. This is the page number 2, in which basically I reconsider everything. It's a little bit more precise because you remember I told you there was an error, I mean, and the formal error is 1, but now is exactly the same. From minus to plus is clear because I bring this on the other part because the idea is to look how it looks like UC of T. But let me reconsider again this with some values. If I put this value here, it's the value which I already told you. R multiply C was 1. For instance, R equal 1 ohm, C equal 1 farad. Here, the transient component is the back transformation of this. Do you remember before I told you 0,5 exponential function up to -1 divided RC. But R multiply C is 1 in accordance with this. This, I can use directly the table as I did, as I showed you before. No? I can use directly the table. Otherwise, remember in math with Benedict, if you don't have the table, you have the table. This means this calculation is useless. But just to show you where the table comes from, you don't need, but I don't know if you remember this partial the composition. In German, it's a Lego. You don't have to learn this because we have the table. But anyway, just to have a feeling where the table come from. If you do, believe me, these calculations, we can demonstrate exactly as before. Before we had 1 divided RC, no? You remember here in the exponent. Now, if R multiplies C is 1, and we can see now the fourth and then the free answer. We have seen this example in dynamical system in a more complicated form, in my opinion. Is more, Tamo, did you see some errors?
No, I just put name for
It's okay. No? If I make mistake, please correct me, because don't trust the professors who does make errors. No? Believe me, it could happen. I already told you many times, the science is the history of the errors. So we are here to minimize them, to reduce them. I don't have the truth, believe me. I try to improve also my knowledge thanks to your contribution. If initial condition is 0, we have 0 here. No? It seems to be complicated, but it's not. It's really useful if you have a higher order of differential equations. Now with the first order differential equation, more or less, but believe me, using the table, using this algebraic calculation, we don't need to learn about the differential equations. May I stop 1 second? It could be that we have a deadline for the IFAC World Conference. Could be that I stop now the EC, I think. No? Or? I would like to pause this one. No?
Yeah.
Okay. We can see here the answer, the total answer, fourth plus free answer. Yeah, if you don't have the free answer, of course, we have just this one. In general, it seems to be complicated, more complicated than the differential equations, but it's not, because you don't have to learn any methods. Just this algebraic, just the table, if you want. Otherwise, you can calculate the signal which we want by hand, exactly what I did so. But of course, we don't need in general. And a part of the calculation is symbolic. Look here. Yeah? No, this is not the same. No, it's not exact. Excuse me. The same as with other consideration. It's symbolic in the sense, symbolically, I transform this expression here. Yeah. But of course, the advantage is more clear for differential equation with higher order. Because with higher order, we have to know something more about the differential equation theory. I don't know if you remember dynamical systems. But anyway, to solve differential equations, even though linear, again, this method here, in this format here, works just for linear differential equations. But even though linear, sometimes it's heavy to find, because we have to know a little bit the theory, methods, cases, and so on. Here, we don't have to learn anything. If you want, you can use directly the table. We have a book table extremely large, for any kind of the most important signals. But the most important signal we will do here together. Okay, let me now look what I can tell you more in detail on this topic here. Because I have seen here something. Let me see. Let me see. Yeah, let me do some consideration here. It's basically it's the same exercise. Let me see if it is possible to tell you. Mhm. I'm thinking. Yeah, 1 second, I come back. To you in 1 second. I'm trying to understand what I have in this slide. Probably it's a question of a student because it's not much commented. The problem is I don't remember the question. This means I have to reconstruct a little bit. If I find something interesting, I will tell you. Otherwise, I will skip. Hmm. No, I don't think so. I don't remember the question. This means we can, at this moment, we can go ahead with another example because it could be. Yeah. Okay, let me consider the mechanical example. Even 1 minute to put inside the material. Okay, page number 1. Okay. And page number 2. Ready? In the slide, in the presentation, you have the same exercise, but with a few considerations. Because in the slide, of course, not so much place to put some many aspects. Okay, let me now consider in this example. I will upload everything. And you can find also in YouTube, but you don't have to. Let me now. It would be better probably to. Okay. Look at this. We have a robot, which I really also for the examination eventually simplified also in the lecture here today is extremely, because if I try to consider not only one joint this here, also this here, also this here, and also the rotation. This is a PhD program. I mean, we will see that we are just considering just 1/4, one joint in this sense, no rotation. And extremely easy for me in order to understand the concept. If you want to consider more elements, of course, it's not the case in I don't know, and Andreas, how many minutes, if for my part, 20 minutes, half hour, something like that. The idea is to understand a little bit the concept. And at the end of the course, we will see some controllers which are applied in automation. Automation means relatively easy controller to be implemented in SPS or the different structure. Look, we have such kind of system, which we will consider just one fault. Question number one, please build the mathematical model of the system represented in figure 1. At the beginning, this is basically the exercise which we have already seen in dynamical system, because the courses are connected. No? I held both, no? But I hold both. Set as a state variable. I don't need to repeat everything which we did in dynamical system, but set is the position of the center of mass. We are considering again an object characterized by its material elements, in our case, Ks and B, elasticity constant, Ks, excuse me, damping parameter, that we are considering here constant, but of course they are not constant, not only. This way to think, to separate elasticity and damping effect, is just a way to see. For instance, with Yanis Amov, we tried to do a totally different approach. We didn't separate this elasticity and damping. We tried to model the characteristic of the material, this phasa system, using the variable order of the differential equation, fractional. I don't know if Yanis told you about this. This is just another way of thinking. I mean, to separate elasticity and damping, just a way to think, just one. But the system, the plasticity of the material. Anyway, this is the model. Please pay attention. It's a way to think, but it's really separable. This probably no. It's just our way to think about material. The word plasticity, I'm not expert in material, you're better than me. Plasticity probably reflect something related to the elasticity and the damping. But it's correct to separate, so it's really, so it's in a way to think. And we have a good result. Forgetting this approach is not present anymore. We will see what Ks and B beta, but in a variable order of the differential equation. But anyway, forget this, but just to have the feeling that to model a material is not a unique one. You have an object to be compressed, to be fixed, and I am thinking that I can represent the model using an elasticity and means plus, adding together the effect of the spring, elasticity, and the effect of the damping. But it's the way to see, not necessarily the best one. Well, God knows the material, the characteristics. It's just our representation, just to give you a feeling about it. Anyway, we have two states. You remember the dynamical system. Everybody did the dynamical system, yeah? The dynamical system is clear. Did you do the examination? Okay. This means we have two states, set and set derivative, position and velocity. I told you a lot about that. This is the model. I told you about this model. If, please pay attention, why this introduction about the way to represent the material? If I think or I model the material considering two, let me say, parallel effects. Parallel is not a good word because it's not necessarily parallel, but both effects, elasticity and damping, elasticity and damping, in combination, in this form, in the linear combination. I can say, linear combination of the spring effect, and together with the damping effect. We know that in accordance with the linear model of the damping effect is proportional to the velocity. The linear effect of the spring is proportional to the position. Of course, you remember in dynamical system, I told you, for instance, here, I didn't consider any static damping effect, friction effect. Remember, I told you a lot about, because here, you don't have here the friction effect or the damping effect static. Otherwise, I have to put, I don't know, B0 SGN of the velocity. Remember this concept that not only we can consider Coulombian friction, in which we have also the quadratic form. Remember this? I told you a lot about this. I'm not expert in modeling of friction effects. I'm not expert. But of course, we can model a different way. Do you remember this Columbian way to do it? I told you in the dynamics. You don't remember? The Columbian way, in which the model is not linear anymore. I have a constant multiplied by SGN, the sign of the velocity. I can continue also quadratic effect, multiply again by SGN of the velocity, because the even function must be multiplied by SGN, because the friction model must be an odd function in order to respect the direction. I mean, the friction is in this direction and in this direction the same. It's an odd function, the friction. Remember this concept, an odd function. But of course, there's a way to think. The same for the spring. The spring is not necessarily linear. At home, you haven't spring. In the last part of the spring, you realize it's not linear. The beginning could be that's quite linear. Compressive, you have a saturation of spring. This means this model is also an assumption. Yeah, we remain with this assumption. But of course, in projects, we can consider different model. Not only this Columbian model, which is based on polynomial approximation, but you have a Lou-Gray model. I don't know if you heard about that. And a dynamical friction model. Anyway, I'm not expert, but anyway, as a system theoretical guy, I don't want to say expert, I work a little bit now with such kind of model. Yeah, the expert of this friction is Professor Arthur. We need a lot about this friction. But moreover, this way to separate is exactly this picture here. The elasticity and the damping, which is reflected in linear contents here, is in a way to think. It's not a unique one. We cancel this totally, and we have a fractional order of the differential equation to be estimated with Kalman filter in order to model better, or in a particular condition, better the plasticity or the characteristic of the material. Okay, just to show you that we can do a lot of things also in this field here. This is the balance from dynamical system is clear. Should I clarify again? No. It's the Newton balance. Assuming that I separate the two effects and I combine in linear form, everything, assumption, as such. The model is linear, we have two initial conditions. If I have, it's easy. I mean, I have always the initial condition, but sometimes, roughly speaking, we say if I don't have, I put 0. But the initial condition must be always there. If you remember Cauchy theorem and math, if you don't have initial condition, we cannot solve the solution. But practically, we say if I don't have an initial condition, I put 0. It's the classical example in the Kalman filter, the observer. Typically, we don't know the initial condition of the system. When we switch on the observer to observe the phenomenon, this means that the observer will put 0. Yeah, again, when I say I don't have initial condition, it's not a correct sentence, but but means zero, no? Zero. This we have seen in dynamical system many times. Inertia, mass multiplied the second derivative, equals the balance of the force. F of t is the unique joint which I am considering in this scheme here. Could be this one, could be this one, could be this one, could be this one. Everything is blocked. It's just one direction. I consider just one movement in one direction, Z. If I consider more than one joint, the system is extremely complicated. So I have to consider more inputs. And we have, in this case, multi-input, single output. Or if you want to control more than one output, we have a multi-input, multi-output, complex. It's not the case of the lecture because it's a project. No? If you have just more than one input, you have to consider the project. Okay, I can tell you also theoretically, but it's already complex here. Now we will see. But I tell you how potentially interesting is this system here for bachelor thesis, for projects, for everything. But of course, in the lecture is, in my opinion, is not only my opinion. Also in technical university, we remain in the basic knowledge because we have to clarify really the basic knowledge. Okay, everything is clear from dynamical system. If you remember, the variable set and set point states the state variable, they are connected with the energy. I will repeat it for you that set is connected with the potential energy. The potential energy here is quite explicit in the spring effect. I would like to say. And the velocity reflects the kinetic energy, the movement. Yeah, I think this is what I would like to emphasize. We can see here in this balance here, we have an energy, an external energy through the input. Then we have the potential energy related to the spring, kinetic energy, and inertial energy. No? Just to add, before to repeat conceptually. Yeah, a little bit. To recap what we have seen in dynamical systems. It's not extremely relevant for this course here, but just to show you the connection, just to and the feeling what we did is nevertheless also here present. Again, everything repeated, but important here in terms of friction effect, in terms of spring effect or the force effect, spring force effect and so on. Very important, Laplace transform. Again, I have an equation. I can transform left, right. Why I can do, I didn't clarify in detail, but it's clear, or that is implicit in the context of the linearity, of the Laplace transform. If A equal B, roughly speaking, the Laplace of A equals the Laplace of B. If I have more elements in the part B of the A, I can separate the contribution because of the linearity of the Laplace, which came from the linearity of the integral, of the parametric integral. Yeah, this is the effect. The linearity basically can be applied. I try to explain quickly again to recall the linearity of the Laplace transform. Therefore, I can say that this expression here in Laplace reflects nevertheless the expression in time. I don't lose information. I don't change the system. Yeah, it's exactly the application. We can see formally how we can work with this Laplace. Very important here to notice S squared. Because basically I apply twice the derivative theorem. Here the condition is equal to 0. I put 0 because otherwise I have to reconsider again the initial conditions, which I told you in a more easy example. I didn't put here because the calculations are a little bit more heavy, but not only. I would like to emphasize the concept as very often the Laplace transform of this transfer function approach is more dedicated to the fourth answer. We have seen before that it's also possible to calculate a free answer. You remember, in the electrical system, I consider an easy example in order to avoid the calculation. Can be done also here. Typically, we do that with the computer. But in any case, I would like to emphasize that this approach is more useful when we need just the external representation. External means without considering the initial condition, or the better to say initial condition 0. Why? If you remember internal representation, consider the initial condition, external representation, the initial condition 0. Very often, in particular in the automation, we are considered just a steady state. Steady state means external effects or external condition. I don't know if it's clear, this S squared. No? This S here is clear because we have the derivative of Z. Here, S squared is there because we have the second derivative of S. This means applies twice, the theorem, the derivative theorem. I didn't show you directly the theorem, the derivative theorem for the equation of the second order, but I told you this is the idea to demonstrate this. If you have a derivative order n is set up to n. Transfer function. Set of S divided f of S. This means I would like to calculate this ratio, which states how change in S. It's a little bit abstract to think about how change in S, because the changes is over time. But in any case, reflects set of S, the change of set of T in set of S, if change f of S. This is the ratio. This is the transfer function. The relationship between, or relation between f of S input and set of S output. This here. G1, or the G of S, I put here G1 because I can consider more than one transfer function in a system, equals set of S divided f of S. This is the goal. It's not so difficult because we have this expression here. And then when we have this, externally, we have a representation of the system, which is easy to be calculated, more difficult to be interpreted. But in any case, G of F reflect the dependence of Z, if you want Z of T, after the back transformation, with respect to F after the breadth transformation, F of T. Let me show you how. Let me rewrite this expression. It's easy because I have to calculate Z of S as the function of F of S. And then I divide. Another concept important is the transfer function does not depend on the input. I don't know if I told you before, but we can see directly from here. Probably I told you very quickly. Because I divided by the input. I show you now very quickly how we can justify this sentence. Look, this is exactly this sentence which you can find as well. If I put in evidence Z of S from here, here, and here, this means I bring on the other side these two elements. No? And then I put in evidence. Clear? These two elements becomes plus on the left, and then I put in evidence set of S. Algebraic. I would like to emphasize how with this approach, S approach, excuse me, we proceed algebraically from gymnasium knowledge, from high school knowledge. Bring on the other side, divide it, no knowledge about differential equations. From here to here is clear what I did from here to here. This on the other part is plus, this on the other part is plus, and then I put in evidence set of S. Just algebraic calculation from high school later. then ready. Because the idea is to find set of S divided F on S. Isn't that? Now we can see the transfer function. If the transfer function is the output divided the input in S domain. But we can see how this is independent on the input. Because I divided by the input. Could be the input, the delta of t. This means f of s is 1, an impulsive force. If the input is in a step, we have here the Laplace of the step. But in any case, I normalize, let me say, by f of s. This characterizes the system. The transfer function characterizes the system. Independent of the input, because I divided by f of s. This I called G1 of s. But if you look at this reflects differential equations, or the differential equation in this case. M, you remember the differential equation was M multiplied Z dot dot plus B multiplied Z dot plus KS multiplied Z. Somehow S is there because of the derivative theory. The order of the polynomial reflects the order of the differential equation. Not only. I would like to say that we have a polynomial expression. Other exercise, please calculate the transfer function G2 equal Vs divided Fs, another transfer function. If I am not interested in the position, I would like to say, I would like to observe, to model the velocity, V of s. How I told you, V of s is the velocity. V of s is the Laplace transform of the velocity, Z dot, is written here, which in accordance with the derivative theorem is S multiplied Z of S. The exercise is to calculate G2 V of S divided F of S. The answer is easy because applying the theorem or the derivative theorem, if Z of S equal V of S, V of S is the velocity. V of t is Z derivative of t, or the Z dot. Not only the position, I would like to observe Z dot, which I called V. Z dot is V. This is Z dot equal V of t. Z dot of t equal V of t. I just recall. How I can calculate it? Easy, because we calculated before Z of S divided F of S. You remember? Z of S divided F of S. Now, if I multiply numerator and denominator by S, I don't change anything, but here in the numerator, I can write Z multiplied S multiplied Z of S equal V. In accordance with the first of the derivative here. This S, which I have here, becomes here, or came here. Because here we have V of S, and here we have S multiplied F of S. But we want to calculate V of S divided F of S. This means I have to multiply numerator and denominator. Let me say I have to multiply by S left and right. This means I will cancel this. We don't have here. I will have S here. I don't know if this algebraic calculation is clear. Otherwise, I can do it analytically, but I think no problem. No, this I called V of S, velocity, in accordance again with the derivative theorem. And then if the request is to calculate V of S divided F of S, our new transfer function, G2 transfer function, I multiply here left and right by S. This means this S will be cancelled, and you have an S here. Clear? This S here states the derivative effect between what? Position and velocity. No? Do you remember? Again, the derivative theorem is reflected here. This transfer function has an S here because the velocity is the derivative of the position. It's reflected with the present of S here. Yeah, I repeated everything again with the explanation. Huh? I multiply left and right by S. Yeah, I cancel because I want to obtain V of S divided F of S. And S appear here. No? The goal is G2 of S. V of S divided F of S. We have an S here. Reflect the derivative between position and velocity. Last exercise that we conclude today. Please calculate the transfer function G3, another transfer function. We can see that the system is quite interesting in terms of outputs, in terms of behaviors. 5 minutes. G3 now is FR divided Fs. It's interesting, this FR is the Laplace transform of the reaction force. This could be also interesting in many applications. What is the idea? The reaction force. If I compress the object, we can imagine that we have a reaction force is opposite. The material don't want to be compressed. If you have any kind of object, let me use this metaphoric expression. The material don't want to be compressed. I mean, I realize that the force against, if you have a ball. I don't know if you want or don't want, but I realize the reaction force, right? Therefore, I say the material don't want. Look here. What is the reaction force? In our model, is exactly the force which characterizes, let me say, the reaction of the material. Minus Ks, multiplied Z, minus beta, multiplied Z. So, it's exactly in the balance the force which is opposite to the F of T. I don't know if it's clear what I intend. I think 2 minutes. Really, a few minutes. This is the reaction force because it's the force against F of T. This is the idea came from here. No? This is the motoric force. The rest is the reaction force. Why not? I can consider so. The material don't want to be compressed. Let me say so. Because of this minus. No? It's opposite to my force. This I call this reaction force. Sometimes in some applications it's important because the reaction force characterizes the capacity when the material will be broken down. We have a limit for this reaction force. I'm not expert. I don't know. Here is Professor Khalifa do such kind of, I don't know who, Bilava, when the material is broken down. But here we can reflect a little bit in dynamical form exactly this behavior. Again, this expression here, basic form we have seen in dynamical system. Now I transform, or I will consider this expression here as Laplace transformation of this reaction force in terms of S, totally abstract, no physical meaning. Don't care about what is no physical meaning, because S is a variable with an imaginary part. Imaginary, I can just to figure out, but the advantage is just to transform and to avoid, also in this case here, many boring and difficult calculations. In fact, look, I can write now my new expression, this form here in which Fr is exactly this. Let me see, because I don't see. If you consider this expression here now, which came for the Laplace transform of this, I didn't put L of, but it's clear, no? If I transform this expression here, I have this expression here. But from this expression here, I can calculate again set of S from here to here. Yeah, again, the clarification just put in evidence that I don't need to clarify this. It's clear, I think. Just to put in evidence. I can lost. I don't have the. I lost the last slide. Let's see. But we can see here. If I consider this and I plug in equation number 3, instead of ZS, I will consider this. I will have this, believe me. Yeah? I will upload that you can see alone in my study. This I will put here. I will obtain this. 1 second, really. I will repeat it for you. I copy it for you here. And then, yeah, I put here on the other side. I put this on the other side. Now, the idea was Fr divided F. Fr divided S. F is easy from here, no? Fr divided F is easy from here. Because I can do some algebraic calculations, and this is the results. Fr divided F at this transfer function. The sign minus is against F of S. The calculation is just algebra from high school. But we can see dynamically how change F R of S, if you want, how change F R of T, F not capitalized of T with respect to F not capitalized of T. And then we can put some threshold when the material is broken down. Now, when the characteristic of the material will be lost. I mean, if I scratch this, there is a point it's broken down. The material cannot react. I cannot theoretically, if I realize the deformation, theoretically will never be the same. But of course, it depends how strong. Okay, we have seen many things today. We will repeat a little bit next week. We will go in depth. And the idea is to, at the end of the course, to learn something about the basic controller which are applied in automation. Now, we have seen also some system recall us and automation system and so on. If you have a question, I am here. Otherwise, yeah, we will see next week at the same time, also in a hybrid form. But if you have time to come here, it's better. But anyway, this is possible also from home. Thank you to be here. I close now the presentation, and I am here for questions.